So for many weeks in a row, we have been talking about random fields of discrete latent random variables. We always assumed a few random variables that were observed and the others whose state we wanted to estimate. So those are called the latent random variables. And we always assume they're either binary or they're categorical, but always discrete. So today I want to start talking about continuous Markov random fields. So here, like the name implies, our latent random variables are continuous. More precisely, they're very often Gaussian, which won't surprise you because it makes math a lot easier. And in this case, this will be called a Gaussian Markov random field, or we will talk about Gaussian conditional Markov random fields, or about a slight extension called intrinsic Markov random fields. And the random walker, you notice I'm name dropping here, is one particular incarnation of an intrinsic Markov random field, and a method that has been pretty popular in the research landscape in the last year or two are so-called regression tree fields. These are also still Gaussian Markov random fields, but we can go beyond this assumption of Gaussianity. And one famous method is called field of experts. And, well, we will do much of this today, so much of the first item today, and a good part of the second item tomorrow. Okay, so this is to tell you a little bit about the landscape. So let me start with an example for a Gaussian Mrf. And as example, I will use denoising. So far, when we talked about discrete random fields, we assumed perhaps two states if we had two classes like foreground, background, or we assumed 10 states for the 10 possible depths in a coarse depth estimate. But if we took a gray value image and if we denoised it to just have 10 gray values afterwards, that would not give a very pleasant impression on us. So here we want a much finer discretization because our human visual system will capture such fine differences. And one possibility would be to still use a discrete MRF with, let's say, 256 states for every random variable, but that will be very costly. You've seen how expensive even our approximate optimization methods were when we were just trying to use a small handful of labels per node. Okay, so this is an example where it makes sense to use a continuous random variable, and we will have a distribution of our true intensity, the probability of x given our observations O, the image that we have acquired, and I can rewrite this as the probability of O given x times the probability of x. And this is Bayes' theorem, so there is also some constant that I'm omitting here. I'm writing this is proportional to. Okay, and Now this is the prior. This is my prior assumption on what do I believe. This is just the distribution of images that I expect to see before I have, made any measurements. Then there is a likelihood term that tells us how probable a given configuration of latent variables is, or how far our observations can deviate from some configuration of our latent variables. And then there is the posterior. And in a Gaussian Mrf, we say that, well, our prior is Gaussian, and we say that our likelihood is Gaussian, and that also gives us a Gaussian posterior. So to put this into a picture, let's assume we have a very simple image consisting of 2 pixels, and we want to denoise it. I'm sticking to 2 pixels here because I have trouble painting higher dimensional spaces. So if I want to incorporate a smoothness assumption here, then I'm putting a Gaussian prior in this space. So this is the space of the intensity in pixel 1 and pixel 2. So this is pixel 1 and pixel 2 here in my 2 pixel image. And well, this Gaussian prior, I can have some expectation of what should its mean be of this image. I'm setting my expected mean to be 0 here, and smoothness means that if I have large intensities in the one pixel, then I also expect large intensities in the other pixel. So this will give me here a correlated Gaussian for which I'm drawing a few isocontours here. Now we know, of course, that intensities really are non-negative quantities and so on. We're ignoring such mundane aspects here. Okay, then I have some actual observation. Let's say my actual observation was here. And I need some model for this likelihood term. So, for example, I can say that my observations O given a measurement x are normally distributed around O with an isotropic, so I hope you can read the difference. This is an O, a small o, and this is a sigma. So what I'm saying here is that my errors are independent and identically distributed, okay? Because x is my vectorized image. So these are the intensities for all pixels at the same time, and O are my vectorized observations. So the formula that I've just written, a statistician would read it as the distribution of O conditioned on x is here given by a normal distribution, or O given x is distributed as, this is what this tilde says, the script n denotes a normal distribution. It is centered on the observations small o, and I have a covariance matrix, which in this case is diagonal. So I assume that the noise is independent here, and the variance of this noise is sigma squared. So if I want to plot it, let me use a different color. I'm using let's say I'm using purple here for this likelihood. So uncorrelated Gaussian noise. will look like this. And the sigma squared tells me how concentrated this is. So let's assume that my noise is not too huge. So I have a fairly concentrated isotropic Gaussian centered on my observation O. Okay, and so now, according to this Bayes theorem, I now multiply my likelihood with my prior. And if you look at the the formula for a Gaussian, so if I take e to the minus something squared and I multiply it with something else, e to the minus something squared, then I obtain something of the same form, so I obtain another Gaussian. And if I try to draw it, it is going to be another Gaussian which is going to have its center maybe somewhere here, and it is going to be fairly compact, but it will still have a little bit of correlation. This will be the distribution of my posterior. So you see that the mean that I have now found, so this is the posterior mean. It is a weighted compromise between my measurements and between the prior between my prior expectation. And the trade-off between these two is given by, well, the variance of my prior and the variance or the precision of my measurements. So for example, if I believe that I have a lot of noise in my measurement, then the distribution that I drew in purple is going to be very wide, and it's not going to have a so then I will tend to more follow my prior expectation. But if my measurement noise is assumed very small, then my posterior is going to be very close to my initial measurement. Okay, so qualitatively, this is what's happening. This was for a 2-pixel image. Now for a megapixel image, we do the same, but in 1,000,000 dimensions. So let me write this. So the probability of x given O, let me give it also with a formula here. So I'm omitting normalization constants, and then this is proportional to e to the minus, here I have the likelihood term first. And then I have my prior expectation next. There we go. And this Q, so normally when we write a Gaussian, we don't write Q here, but we write the inverse of the covariance matrix. Yeah, so usually when you write this formula, you write something like this. But today I am not using the inverse, but I'm using here the precision matrix directly. Okay, so Q is called the inverse covariance matrix or the precision matrix. Precision matrix. The term comes from this measurement idea, because so if we have a very precise measurement, then its variance is going to be small. Yeah? So small variance corresponds to large precision, and vice versa. Now, what's good about this model? It is tractable, as we will see in a moment. What's bad about this model? Not very good. So, I can, not very good, I can explain this in terms of pictures, or I can explain it in terms of, or I could show it in terms of numbers. So let me show you in terms of pictures. Here is a realization of a Gaussian Markov random field. So we have defined a distribution over images, and this would be a typical representative image. And well, it is a scalar image. It is just shown here with the false colors, and that is not a very good model for the kind of natural images that we see. So, and the consequence of us having such a bad prior is that if we now benchmark this as a denoising method, it's not going to be nearly as good as many engineered methods. However, it's a stepping stone for very competitive methods that I will show tomorrow. And in fact, the current best method published at CVPR 2 weeks ago is a version or an extension of a Gaussian Markov random field. Okay, so I said, so, by the way, why is it not such a good image model? Well, one reason is that you can already see from this single realization here, there's not a single edge in there. We have a very smooth variation, and in natural images, edges really matter. And so we have a discrepancy between what the model or what our expectation says and what we really have in the world, and this leads to suboptimal results. Okay, so I argued it's tractable. Let's look at this. So I will again argue about energies rather than probabilities. So I can ask for the maximum likelihood estimator. No. Wrong. The map estimator. And so I want to find the configuration of latent variables that maximizes this posterior, or equivalently, I can take the log and take the negative of it, and then minimize a quadratic expression. And I'm again calling this an energy which depends both on my latent variables and on the observations. Okay, now I'm going to be super explicit. I know you all know how to factorize, a quadratic expression, but I want to stress the similarities to what we had before when we were discussing the discrete Markov random fields. So I can say that xi squared yes? Yes, we take the log of the previous expression and we take the negative of it, and then we end up something that we want to minimize rather than maximize. Okay, so this is going to look very familiar to you. This is what we previously had called a potential psi ij of xi and xj, and this is what we had previously called a unary factor or a potential psi I of xi. And you know, this already tells you it already tells us something about the sign that I want in this Q here, because so if I plot xi, xj, if I plot the product here of xi and xj, I'm showing equicontour lines. And this is positive, this is positive, this is negative, this is negative. So I've plotted here xi times xj, but we wanted to encourage similar intensities. So similar intensities should have low energies. So, but here on my diagonal, I get positive values rather than negative ones. So that tells us that these elements qij here, that these off-diagonal elements of Q, that they should be negative if I want to encourage smoothness. And now I have not yet said what exactly this matrix Q looks like. We have here a sum over all I and a sum over all j. So if I have my nodes here, I still have the choice. If I'm now looking at, let's say, if I'm looking at this node here, our standard choice for the discrete MRFs has been to take as neighbors only the directly adjacent pixels. But I could, in principle, you know, have, so it is also quite typical to go, okay, let me use different colors. So black was the 4 neighborhood. Let's say I'm using blue to also indicate this type of interactions here. This would be an 8 neighborhood, which is better than the 4 neighborhood in the sense that it reduces metrication artifacts. What I mean by that is this 4 neighborhood really likes to have, for example, edges in the image that run along horizontal or vertical lines. But if an edge in the real image happens to not go in steps but at some angle, then it is often better to use an 8 neighborhood, which however has the cost of increasing your model. You have more factors. And now of course you can make this depend on further points, like this one here and this one here and this one there. Or if you're, why not? You can even have it connect to pixels that are even further away. This would be called highly connected. If every random variable is connected to many others. But note that no matter here whether 4 neighborhood, 8 neighborhood, or highly connected, all of these are only pairwise factors, the way I've drawn it here. And this is a different dimension in which I can choose model complexity by using factors, for example, let's say like this. Here I have factors depending on 4 tuples of random variables. And by convention, any factor that depends on more than 2 random variables in image processing is called a higher order factor. Because it has a scope encompassing more than 2 random variables. Okay, so this is a small excursion here, and I want to stress the difference of the first one was highly connected or not versus higher order. Now with these Gaussian Mrfs, can I become highly connected and can I be higher order? Question to you. Yeah.
So I would say, since we have the structure of the covariance matrix, we can be highly connected.
Mm-hmm.
So if we only have elements on the diagonal, we only self-connected, and the one right next to it is the neighbor thing. And to have the higher order factors, I don't think this is possible.
Exactly. You're right. So higher order, again, let's look at this energy function here. On the left-hand side, I'm writing an energy that's depending on all random variables, because this is my entire image vectorized. But then if you look at the form of this expression, it only depends on up to pairs of random variables. So a Gaussian Markov random field, it can be highly connected, but it must always be, it is just pairwise. It can only accommodate pairwise factors. Okay? So Gaussian Mrf can be highly connected, but not higher order. Or if it were, it wouldn't be Gaussian Mrf. Now, the standard choice for Gaussian Mrfs is to use the same modest neighborhood that we had in the discrete Mrfs. And then, let's look again at the formula above and draw the corresponding probabilistic graphical model here. This is the image which at the end of the semester will be burned into your retinas, because we've seen it so often. So we have here a latent variable xi, we have an observation oi, we have a latent variable xj, and then we had the unary factors psi I, or potentials, and the pairwise potentials psi ij. So I want to stress that the factor graph looks exactly as we had before. It's just that this time the scope of the random variables and the nature of the potentials differs. But that means it is a member of the same family of distributions that we have already looked at previously. So distributions that factorize in this particular manner over over their constituent random variables. Okay, so we have this minimization problem here. We saw that it is an expression that is quadratic in x, and we know how to solve that. So to minimize, I take the derivative of this with respect to x, and I set it to 0. So if I want to collect terms here, I can say that on the right-hand side I have O, and on the left-hand side I have X, and I have sigma squared times Q plus the identity matrix. And so sigma squared was just a scalar number. This was a scalar. This was our precision matrix that codifies what kind of interactions we use. And if we use something like the 4 neighborhood or the 8 neighborhood, or even even larger neighborhoods, this is still going to be very sparse, because you only connect every random variable to its however many neighbors close by, but not to every other pixel in the image. And this here was just the identity matrix. Okay. And on the right-hand side are, again, this is not a sigma, but these are the observations. So the identity matrix is sparse. The other matrix that I added to is also sparse. So this entire thing is sparse. And I could now rewrite this as x equals the inverse of what we had on the left-hand side. But this is a bad idea, because this thing is going to be dense. And remember that this is a very big matrix. So if we have n pixels, this is an n by n matrix. So a matrix with 1,000,000 times 1,000,000 entries, and you don't want to represent that densely in your memory. Or if you do, then I want to have your computer. So it is actually better to solve for x in this form here. To find the map estimator. And to solve this, you can, for instance, use the sparse LU decomposition, or you can use iterative solvers. So, we had a quadratic expression, so we are only looking to find the bottom of a parabola. However, one with very many dimensions. And iterative methods, it's just some kind of gradient descent method that will take you to the bottom of this parabola as quickly as possible. Okay. Now there's more to say on this precise choice of Q. So far we only argued, do we want to take 4 neighborhood or 8 neighborhood or so, but what are the elements of Q going to be? We argued that the off-diagonal elements better be negative if we want to encourage correlation. One typical choice of Q is to use the graph Laplacian, and I want to motivate it. So for instance, I could say I want to choose Q so as to penalize the squared finite differences between adjacent pixels, between adjacent pixel values. So I could say that I want to use the following. Now I'm using the tilde here to say that I'm only summing over pairs I and j that are adjacent. And I may, for example, want to say here I want to penalize this squared difference between adjacent pixels. And then I have my data term. And I'm going to further decompose this into horizontal and vertical neighbors. So here I'm looking at the horizontal neighbors. And then I'm going to look at the vertical neighbors. Plus the data term. And now we can try and express this in terms of matrices. So for example, to find the horizontal neighbors, I can use the finite difference operator in the horizontal direction and apply it to my vectorized image. And then, because I want this square, I have to take the multiply with the same vector transposed. Plus data term. And this I can rewrite as X transpose, and then I have the DH plus the dv times X plus the data term. And now I can argue either in terms of matrices or in terms of operators. So if I argue in terms of matrices, then, for example, my horizontal finite differences operator is going to look like this. I can take a +1 here and a -1 there. And now I also have the vectorization of the image, which it's a bit tricky to draw this correctly here. So essentially I'm having a matrix with a single off-diagonal element and so on. And if I multiply it with its transpose, then I find that I obtain a second order derivative. Yeah, so if you apply dH transpose to itself, you will get filter elements that look like this. In the spatial domain. So now in the domain of the unvectorized image. And dV transpose dV has elements -1, +2, -1 in the spatial domain. And if we add these two up, then we get a matrix which I'm going to call L for graph Laplacian. And this L looks as follows. In the spatial domain. So on the Cartesian grid, this is like taking second derivatives in both directions, or it's the negative of the curvature, it's the sum of the negative curvatures in both dimensions. But the graph Laplacian can also be defined on arbitrary graphs, not just on Cartesian grids. Okay, so the and this was meant to be an addition of these two kinds of elements. So what I find overall, if I want to have a Gaussian Markov random field that penalizes quadratic deviations between neighbors, then I get an energy function that looks like this. This is the smoothness prior, and this is the data term. Okay, now we have, of course, plenty of choices how to generalize this, and we'll look into these after the break. One obvious thing we're going to do is to make this Laplacian also depend on the observations to obtain a more expressive model.